perhaps by many forgotten by now, but Intel had long been the undisputed king of the semiconductor industry. As CEO Brian Krzanich, or BK, said in 2014, "The mission is to really utilize Moore's Law. We have it. We believe we lead at it. We drive it. We define Moore's Law as a company." During its heydays of technology leadership from around 2000 to 2015, Intel introduced the three main transistor innovations of the last few decades: strained silicon, high-K metal gate, and the 3D FinFET transistor. Each of these innovations marked a major change from the textbook transistor. Without these, Moore's Law would have ended generations ago already, and Intel in fact had an over 3-year lead on everyone in introducing these technologies. This made Intel, the company behind Moore's Law, arguably the most important and most innovative company in all of the technology industry, for without semiconductors there simply would be no tech. However, at the 10 nanometers node, which is equivalent to TSMC's 7 nanometers node from 2018, Intel fell behind due to a more than 3-year delay. The main reason was low yield, mostly because of ambitious scaling targets and the lack of EUV lithography, which itself was delayed by many years. Simply put, without high yield, it is not economically viable to go into commercial manufacturing. For example, if yield is only 10%, then Intel would need up to 10 times as many fabs to produce the same manufacturing output compared to its previous nodes. Going into a bit more detail, actually Intel had originally envisioned that 10 nanometers would be the node where it would massively extend its process leadership, especially with regard to transistor density. Due to the delay of EUV lithography, the industry had developed multiple patterning schemes. As the name implies, this technology uses multiple exposures to produce a feature with a smaller size than a single exposure. It turned out there are two versions of multiple patterning. In the most simple approach, indeed the wafer is exposed, for example, twice. This is called litho-etch, or LE to the power n. This is what the foundries did. However, Intel had a more clever way of going about it. This technique is called self-aligned double or quadruple patterning. In theory, it is much cleaner and technology, and each step reduces the minimum feature size by 2x. Hence, with Intel adopting this technology instead, it saw a chance to leapfrog the competition in the absence of EUV. Together with a few other novel technologies, Intel was planning to increase the logic transistor density by a remarkable 2.7x at 10 nanometers, far surpassing Moore's Law. However, as mentioned, Intel struggled for over 3 years with the yield, and even after the node entered manufacturing it was still below previous nodes. Overall, Intel called this set of technologies to accelerate transistor density scaling hyperscaling. As mentioned, it was introduced because of the absence of EUV. The downside of multiple patterning in both schemes is that it requires more steps to produce one feature. This increases the cost, and hence this endangered the economical side of Moore's Law, which is that Moore's Law results in a decrease in cost per transistor. Without a lower cost per transistor, chips might perhaps get 2x more transistors, but they would also be 2x more expensive. As Moore's Law is inherently an economical law, if the economics of scaling broke down, then Moore's Law would effectively have ended, even if transistor could still become smaller. To remedy this, Intel indeed tried to compensate the higher manufacturing cost by increasing the amount of scaling. Following is what Bill Holt said in 2013. When we began looking at the increasing wafer cost, we had a somewhat substantial debate as to what should be that point for 14 nanometers on the cost per transistor curve. And when confronted with a substantial increase in wafer cost and a historical trend of density scaling, we had considered whether we would have to begin to bend this curve towards the end of Moore's Law, and there was in fact a substantial opinion that it was now time to start bending the curve. But we stepped back and we got a point substantially better than what we had asked for. We are in fact accelerating Moore's Law. As a side note, since the 10 nanometers delay happened just as AMD was nowhere during its bulldozer failure, before Zen and Ryzen, some people thought Intel had simply stopped innovating. However, this couldn't be further from the truth. Even without any competition, it would still be advantageous to continue process node development to decrease the transistor cost, but perhaps not increase the transistor count as much. As mentioned, Intel had planned to transition to an 8-core CPU in 2016 already on 10 nanometers, nearly a year before AMD launched Ryzen. Intel ultimately tried to make up for the 10 nanometers delays by increasing the core count on 14 nanometers, obviously increasing the chip area and hence manufacturing cost. Or as Bill Holt said in 2013, if Intel stopped innovating it would be because it couldn't keep up with Moore's law, which is indeed what happened. Well, let me start with saying that I'm not about to start predicting the end, since anybody who's tried that has been wrong. So I'm not going to try that. The other thing that I'd refer back to is, Craig many years ago said when asked this kind of a question is that, yes, there's a wall out there, somewhere potentially, and he was going to run into it as fast as he could. So we have no intention of slowing down. If we slow down, it will just be because we can't keep up. So we'll see. The goal is to keep pushing that wall out, and that's what we're doing right now. And as far as hitting, we're not going to slow down because we see it on the horizon. In summary, Intel had planned to launch its first 10-nanometer CPU, the 8-core Cannon Lake, in 2016, featuring a transistor density of 100 million transistors per square millimeter. For comparison, the 10 nanometers process of Samsung and TSMC, which was introduced in 2017, only had a transistor density of 50 million transistor per square millimeter. Hence, Intel would have been 1.5 process nodes or 3 years ahead of the competition. However, due to its 10 nanometers yield issues, instead TSMC and Samsung took process leadership in 2017 with their 10 nanometers nodes, which TSMC further extended with its N7 node in late 2018, over 2 years behind the original Intel 10 nanometers target. Intel reached parity in late 2019 as it finally got 10 nanometers yield up, but TSMC took over again with N5 a year later, with a density of 135 million transistors per square millimeter. So, after 10 nanometers, Intel had planned to catch up again with its 7 nanometers node in late 2021, which has since been renamed to Intel 4. However, Intel encountered similar issues as at 10 nanometers, and instead the first product, Meteor Lake, only launched late last year with Intel 4. This implies a 2-year delay, and also 3 years behind TSMC's process leadership. Although it should be noted that Intel 4 is actually closer in density to TSMC N3 than its N5. The 7 nanometers or Intel 4 delay was announced in mid-2020. Shortly thereafter, in early 2021 Intel replaced Bob Swan, its CFO-turned-CEO bean counter, by Pat Gelsinger, a long-standing Intel veteran, rejoining the company from VMware. Pat Gelsinger was tasked with a monumental turnaround after these 2 major consecutive process node delays, or even 3 consecutive delays as 14 nanometers had also been delayed by about half a year, due to yield issues as well as that was the first node to use double patterning. Is Pat Gelsinger and Intel finally succeeding in turning the ship? Or has Intel only fallen further into irrelevancy as other companies such as ARM, TSMC, and NVIDIA have taken over the semiconductor industry? Has Intel encountered further delays and yield issues, or has it miraculously recovered what was once a truly world-leading TikTok development engine? Stay tuned for the next video.